Simon. So myself, I'm Praveen, CEO and founder of Sumandra. So we are working on digital twinning of composite manufacturing and also structures as well. So it is mainly the AI-driven composite, mainly focusing on aerospace and also some other areas. So this is where the brief contents of the today's presentation. I'll start with the some introductory part of what is digital twin, and people who are not familiar with composite, I'll briefly mention about the systems and then couple of application in automation and energy as well. And also there will be some challenges and then simulation as well. And finally, I will address some fatigue assessment. So this is what the brief so you can see that there are mainly four elements, which is the physical system on the left hand and then right hand side, that you get a data from composite manufacturing and also you get a data from real time. You take those for simulation, then testing, and finally those data will be processed and then used for testing and presented to the user. And you can see on the left hand side, I have briefly mentioned what those really the physical system looks like. So mainly the composite fuselage in aerospace, in energy, wind turbines, and then chassis in automotive and buses. The virtual model include kind of finite element simulation, and finally sensor data integration for real-time assessment, and finally the real-time monitoring by AI prediction and then control loops. So the composite materials. So if you are not, I hope most of you familiar with the composite material, but I'm mainly focusing on fiber reinforced composites. So basically, the composite is actually the combination of two materials when they are combined together to form a new improved version of a material, so that we get a better properties. So in this case, the fibers is mixed with matrix. So the matrix is nothing but plastic, so it gives a better tensile strength. And finally, we get a composite in different fiber orientation. So they are at the different scale, like we can at the global scale and then also macro scale, meso scale, which is between the layer, and then finally at micro scale within the each layer. So this is the overall view of 23/24/7 digital twin architecture, and then each entities. So introducing to the aerospace, digital twin, again covering back to the basics. It was coined by in NASA in 2010. So when they started this Apollo 13 spacecraft program, and and it can be defined as personally dynamically evolving model, I have to say, because the finite element what we see in usual life, it is a static model. So because it is not evolving based on the fatigue loading or any kind of load onto it. So that is the reason I am mentioning specifically as because it is representing the live the picture of the model. So it mirrors the real-time behavior of the system. And so this the composite structure could be used anywhere in not just in aerospace but also in automotive. I will briefly cover later onwards. So composite materials, so they cover up nearly 50% of the modern aircraft. So it is very much necessary and then essential for the aerospace to understand like how really happening through the digital twin. So some of the case studies I have got here for you. So go back to the 21st century where the NASA conducted S-33 spacecraft. So they had this, completely recyclable composite X-33 spacecraft. So they spent nearly 1 billion of dollars in collaborated with Lockheed Martin, understanding how can we recycle, completely recycle the material used for the spacecraft. Unfortunately, there was some leakage in liquid hydrogen tank. So when they started commissioning the project, they found like there was some leakage in the tank. This this problem is not just the first time. This was also the problem which had occurred earlier in Apollo 13. If you remember, the failure of that Apollo 13 in the space was due to there is some kind of recurring problem. We have to chase this, and of them, understanding the digital twin and coining the term. The cracked window, you might have seen, although there, today's incident you have seen in Bangladesh where F-7 flight is crashed and also jet flight 171 Air India. But although I don't want to clearly go into them because it's too early for clearly describe the failure assessment and the structural integrity assessment. Whereas I'm covering here the Nippon Airways where there were some cracks in the structure, which is mainly due to the fatigue assessment. I mean improper fatigue assessment, and also the door plug which fell off from the Alaska Airlines in 2024 last year. So the main problem of these is not properly considering the manufacturing defect and also the vibration issues in the structures. And also you can see on the left hand side where there is a the flight where the wing was completely ripped off while it was flying in the sky, and that was a terrible moment for every passengers and also crew as well. So this is the main bottlenecks the digital can address. So which is the outdated design and optimization. So there is no inclusion of residual stress and then defects uh, in the present modern design, and which is leading to post-production problems. And finally, this is leading to unknown damages and the total strength leading to unexpected failure and then increased downtime. And there is also no proper tools which is kind of exorbitant. Even whatever you see, the ANSYS and Abacus, the engineers they think like it is mostly for research, but not for daily understanding and designing structures. So some of the manufacturing issues what you can find in composites are spring back mechanism. You can see on the top right. So when you prepare any geometry or any manufacturing any geometry, they go out of shape because it contains some kind of residual stress, and these stresses are major culprit for structural failures. And some other failures are cracks and then delamination, what you see in second and third, and finally the fourth one, which you can see in pipes as well and pressure vessels. So the smart manufacturing solutions, what the Sumandra is addressing is the total stress approach, which is manufacturing and then operational stresses and defects. We are going to measure those manufacturing stresses and then operational stresses as well, along with the defects upfront to understand how it is impacting the strength. And finally, we do monitor the structure through sensors, and thereafter we provide the digital twin at the end user through the cloud. You can see how it is impacting. It is around 40 and 30% of maintenance cost can be reduced, and up to downtime of 50% is saved. So not just in application, I will just touching just in one slide about the automotives as well.
30
so the
seconds
market
left,
of
please,
this
Praveen.
automotive is also huge, not just
30 seconds left, Praveen, if that's okay.
Sorry, Simon, how much?
30
Okay.
seconds.
So there is couple of sure applications in chassis mainly that we are trying to address the issue, and in energy the turbine where the wind blades are mostly susceptible for the fatigue use. You can see in the image the pressure vessel used what I previously said in NASA X-33. Unlike metals, these consist of the fibers. You can see it's very non-homogeneous. The strength what is usually used in metallic not for this, and that is why the composite digital twinning especially is very much important. And you can see the AI driven simulation, how it is going to help us in understanding all those 4 defects what I said in previously. So in this slide, in this presentation, I'm mainly focusing on the modeling and simulation part, which is the primary layer of the digital twin reference architecture. And we are also using surrogate modeling for speeding the simulation. And this is some of the simulation and then validation what we are trying to understand. We are including some couple of experimental methods to validate. And these are theoretical. I don't want to further go deeply into this fatigue assessment of how the structure fails related to the what the case studies I have previously mentioned. Yes, overall, digital twin is really shaping a composite, structural design, and we really need in the future structural analysis. and it is providing a predictive modeling and then cost efficiency and then improved structural safety. And the main problem consists here is embedding sensors. Till now, the manufacturers are really scared of embedding them because they don't want to, include something, the new sensors which is going to trouble them, and which will slow their bulk manufacturing. And simulation and validation is one of the major challenges in the structure. And
Praveen, we've got to wrap it
yeah,
up now, if
and we
that's
need a
okay.
yes standard framework. We need a standardized framework for overall digital twill in composite structures. The fun fact is we can also use this technology for sculptures as well. Whatever the sculptures we can see in this present day, it's the metals. If we use the polymer composite, we are really recycle them and then make them more sustainable.